Alright, welcome back. Today we're going to look at another section from 4.1. We're going to focus in on example 4, which is to determine the extreme values of a specific function. Previously we used the graphs and we looked at taking the derivative and setting it equal to 0, which is very similar to what we're going to be doing today. So now we're going to look at a little more complicated like functions, not just a basic function with an exponent, but now we're going to be looking at a square root in the denominator. So we're going to have to include some domain restrictions, but that's okay. It's not that hard to work around. The first thing I want to do is I want to look at the function that we're working with, which is f of x equals 1 divided by the square root of 4 minus x squared. So right off the bat, I want to point out the domain restrictions on this. So the restrictions on our domain are, this is the domain of f, are from -2 to 2 with an open set of parentheses. Now this is very important to notice because this means that we're not going to have endpoints, so the extreme value theorem will not hold here. The next thing I want to do is I want to rewrite this function so it's a little simpler to take the derivative of when we go ahead and take the derivative. So I'm going to write this as 4 minus x squared to the -1/2. It's very good to get in the habit of writing that with that exponent. Okay, so this is a complicated looking function. Top of my head, I'm not really sure what it looks like. So this is what I recommend. I recommend to look at, what do you think? The graph. So I recommend to look at the graph. Let's go ahead, you can put that on your calculator. I'm going to go ahead and pull it up here on GeoGebra. Get rid of all this nonsense. Okay. So right here, this is the graph of, oops, wrong tangent line. Here's the graph of 1 over 4 minus, the square root of 4 minus x squared. It kind of has this U shape, and you can see as far as I zoom out, it really doesn't get past 2. So that shows that our domain is from -2 to 2. So I'm actually going to go ahead and I'm going to take a screen clipping of this. Oh, look, there it is. I'm going to go ahead and I'm going to copy that into the notes. I would recommend maybe drawing a quick sketch of this just so you have it, because I'm going to mark this up a little bit. So right here, if we look, it looks like a minimum. So this looks like a min of 0.5 at x equals 0. And you can see right here, just based off this graph, it looks like we have a max at x equals 2. But as we notice when we zoomed out, f of x is not defined at x equals -2 or x equals 2. So that's going to be kind of a foreshadowing to we won't have a maximum for this problem. Okay, again, because the extreme values theorem says if we have a closed interval, we will guaranteed have maximums, but because it's not a closed interval, we're not guaranteed that. Okay, so like I said, it looks like we have a minimum at 0.5 at x equals 0, but graphs can be deceiving, so we need to check our algebra and actually make sure. So we take f of x, which is equal to 4 minus x squared to the power of -1/2. Now the way we find mins and maxes is we take the derivative and set that equal to 0. So let's do that right now. Let's take the derivative. We get -1/2. 4 minus x squared to the -3/2, and then times the -2x using the chain rule. So my negatives are going to cancel off, and my 2's are going to cancel off. And we're going to get that this is equal to x divided by 4 minus x squared to the 3/2. So what we need to do now is set this equal to 0 and solve. So you get that x is equal to 0. So this right here is a critical point. Let's keep in mind that at 2 and -2, at x equals -2 and 2, f prime of x is not defined. However, let's also keep in mind that these values are not in the domain. So, we don't really have to worry about them. So now I recommend we make that sine chart that I like so much. F prime of x. And sine, this is S-I-G-N. Sine, not sine wave. Okay, so I'll draw this. And I'm going to put -2, 0, and 2. Keeping in mind that it's undefined at these points. I just need them for my endpoints. And I need to pick a value between -2 and 0, so I'm going to pick -1. And I need a value between 0 and 2, so I'm going to pick 1. So now I need to evaluate it at -2, -1, 0, 1, and 2. Basically, I need to evaluate it at all of these x values. Now 2 and -2 are done because they're undefined. So I'm going to do f of 0, and I'm going to get 1 over the square root of 4 minus 0 squared, which is 1 over the square root of 4, which is 1/2. So this means it's either a maximum or a minimum. But I need to figure out, is it a max or a min? Well, looking at the graph, we know it's a min, but let's just do it with algebra. So using algebra, we're going to take the derivative at a -1. So you get -1 divided by 4 minus -1 squared to the 3/2. So you get -1 over 3 to the 3/2. I don't even have to keep going. All I care about is that this number right here is negative. Not necessarily the numerator, but that this whole thing is going to be negative. So that tells me that this thing is going to be going down. Now I need to plug in 1 into the derivative and see what I get. I get 1 over 4 minus 1 to the 3/2, which gives me 1 over 3 to the 3/2, which this whole thing then is positive. That's something that this thing is going to shoot up, which tells me that this right here is a minimum. Okay? So now we're going to write our answer, all nice and neat. We're going to write that there is no maximum since the domain is -2 to 2, which is an open interval. So this is why we do not get a maximum. And we have an absolute minimum of 1/2 at x equals 0. And that's really all there is to doing these, is just to determine maximum mins. I would definitely advise to use the graphs for help, but be able to show with calculus because I'm going to require that. Okay. So now what I want you to do is I want you to take this example and try to find the max and mins where they exist. Take a second right now and try to figure that out on your own. Okay, so let's go ahead and let's take a look at the graph. Before we do anything, I want to look at the graph and I want to understand what this thing looks like, because off the top of my head I know it's x cubed, so I know the general shape, but I don't really know what the graph looks like. So just looking at the graph right here, I can tell you right away there's a local max right here and a local min right here. And as I move this along the tangent line, I can see the derivative is positive, and then as this point moves, oh look, it becomes negative. So we had a max and then negative to positive, so we have a min. Again, the derivative right here is positive, it becomes negative, so we have a min. And then negative to positive, negative, it becomes a max. So the derivative is positive, and it becomes negative, so we have a max. It's negative, and it becomes positive, so we have a min. Okay. So now let's do this using some math. So the first thing I want to do is identify the domain of my function. Well, this is x cubed, so the domain of this, oh my goodness, the domain is negative infinity to infinity. That's the domain of this function. So keep that in mind that we might not have an absolute max, we might not have an absolute min because our function extends for all x values. So what we need to do is take the derivative. You get f prime of x is 3x squared minus 6x. And to find those critical values, you go ahead and set the derivative equal to 0. And then you solve. So you get 0, you get x equals 0, and x is equal to 2. So both of these are my critical values. And so what I need to do now is go ahead and make my sign chart. So I'm going to write f prime of x. Here I'm going to put negative infinity. Draw a big line. Here I'm going to put 0. Here I'm going to put 2. And here I'm going to put positive infinity. So what I need to do now is pick points in between. So I'm going to pick negative 1, 1, and 3. And I'm going to evaluate the derivative at the ones that are circled in green. I mean the regular function where they're circled in green, because I need to know what the value of those are. So I get f of 0 is equal to 0 cubed minus 3 squared plus 3, and you get 3. So this value is 3. I get f of 2 is equal to 2 cubed minus 3 times 2 squared plus 3, which is 8 minus 12 plus 3, which is, make sure I did that right, negative 1. And now what I want to do is in the orange, I'm going to evaluate these at the derivative to determine increasing or decreasing. So f prime of negative 1 then is going to be 3 times negative 1 squared minus 6 times negative 1, which gives me 9, which is a positive number. So this is increasing. And then I'm going to use f prime of 1, which is 3 times 1 squared minus 6 times 1, which is 3 minus 6, which is negative 3. So this is a negative, so it's decreasing. And then f prime of 3, which is 3 times 3 squared minus 6 times 3, which is 27 minus 18, which is 9, which is again a positive number. So that tells me that this one right here is a max, and this one right here is a min. So now all we need to do is make our conclusion. And we're going to write that there are no absolute min or max. So at no absolute minimum or maximum. We're going to write that it has a local minimum of negative 1 at x equals 2. We have a local maximum of 3 at x equals 0. And so this would be our answer, and based off the graph, we know that that's correct. And that's it. That's how you find local mins, local maxes, and absolute max and mins.